this is it. Welcome to this session. So this is going to be an interesting conversation, we've had a couple of good conversations so far. And really this is a continuation of what Rob spoke about this morning, and then what I touched on as well as to how we can use genomics in a more planned and coordinated way to tackle some of the big problems or big challenges, I suppose, that we have in our industry. And so Rob's going to go through some of his thinking and give you a little lecture in quantitative genetics and economics, and present the concepts really, and then we'll have some open discussion, because this is a challenging topic, and there's some gnarly twists in this that we've got to work out how we can go about some things. So nothing's a done deal. But anyway, with that introduction, I will hand over to you, Rob. Take three. We might be getting all right at the end of this one.
Well, we could have a little wager on that, Jace. I don't think the microphone's working, is it? That is. Sorry. This thing. I'm not quite sure what to do. Anyway, look, I'll try and make this clear and so forth. This is kind of, there's a couple of slides that I'm going to go through that I used this morning. What I'm really going to talk to you about, or try to get across, is the idea that we can think about an optimal level of amount of investment in phenotyping, an optimal amount of phenotypes for the things that we want to improve using genomic selection, and then a way of sharing the costs of that phenotyping. And it's going to be reasonably quick. I hope it's clear enough. But the fundamental challenge for genomic selection is getting the right amount of quality phenotypes for the things that matter to us. Just a reminder, the genomic selection model is pretty simple, really. Up the top there with the green sheep, we've got the animals that we're measuring the phenotypes we're interested in, and we're reading their DNA, and they establish basically a reference library for us. If we then go in and genotype the animals down the bottom here, the white ones, the animals that do not have their own, they have no measurements on them themselves, as long as we've got a reference population, we can work out the genetic merit of these animals down the bottom with a level of accuracy that's determined by the size of the reference. So to do that, we're essentially running a big investment program. We invest in phenotyping and genotyping up in the reference, that's the red arrow, and we harvest the value in either rams or commercial lambs and ewes down the bottom. And in a sense, my approach is to try to think about that whole picture and work out how to optimise it. And those are the questions. So the first bit, I just want to get across the idea that we can think about the optimal level of phenotyping. I'm not going to read through this, I'll just pull out the highlights, but the point is here that it is possible to work out the optimal level of phenotyping. We know phenotyping costs money. We can work out how much money we can make from genetic gain, how much the industry makes from genetic gain, and we can find an optimal level of phenotyping. In my little example, I've just modelled two traits. One's easy to measure, one's hard to measure. Anybody who's just tracking that red thing around is going to be shot, because that's a carryover from an old recording, so I won't shoot anybody, it's okay. But it's kind of a distraction, and I've just made it a bigger one. But the point is, this is just about modelling two traits, and all I'm doing is varying the accuracy that I've got for each trait in a genomic reference population, working out from that accuracy how much genetic gain I can get depending on the value of the traits, how important they are, and then I can back solve from the accuracy for how many records did I need to get that accuracy, If I know the cost of the phenotypes, I can work out what did I have to spend on phenotypes. I can compare that with the return and work out where do I maximise my profit. So in this case, as I said, I've done two traits. I've worked out, modelled their genetic parameters, the correlation between them. I can calculate the response to selection at any given combination of accuracies, and then I harvest the value of the genetic gain across a commercial population of different sizes. This is just to show you what the results for response to selection look like. Don't worry too much about the values in the coloured cells. They're just how much index gain you make from one round of selection. The important point is we varied the accuracy for trait 2, which is across that way, and it goes from 0.158 or 16% through to 0.848 or 85%. And for each of those numbers, the corresponding number of phenotypes to get that accuracy is in the first row. So to get 0.848 accuracy for trait 2, we'd need to have 128,000 records in our reference population. Similarly, going down, that's trait 1, we're increasing the accuracy, and you can see we've gone from 27% to 94%, or 0.27 to 0.94, and the corresponding numbers are in the very first column, goes from 1,353 records needed down to 136,000. So that's all I've done is vary the accuracy for the two traits, work out how much response is possible, that's the number in the coloured cells, and then because I know the numbers of animals that are being recorded to get the accuracy, I can calculate the phenotyping cost. How much did it cost me to get that accuracy? And from that and the size of the population, I can then work out, well, how much money am I making? What's the returns and what's the cost? Please don't spend very much time looking at this. It's just simply to reinforce the point that I can work out the point of maximum profit for across that table of accuracies and responses for different size commercial populations, 500,000, 1 million or 2.5 million animals a year. I can do it for different genetic correlations, and I can work out the point or the combination of accuracies that gives me the maximum returns minus phenotyping cost. And once I know that, I could then make decisions about, do I want to be at that point? So all that's really showing is we can model all this stuff. It's easy to show that if you've got a bigger commercial population you're harvesting the genetic improvement across, then your profit's going to go up. Basically because once you've created the accuracy, you're just collecting the return from it over whatever your commercial population is, and if that's bigger, you're just going to make a bigger profit. So that's all that slide is doing really. And this slide is simply saying that for any set of parameters, there will be an optimum level of phenotyping. The axis across the bottom is the amount of money we're spending on phenotyping, and you can see in my model it's gone from $0 million to $16 million, and up there is the 5-year profit, and that's profit after the investment. But the important point there is that there's a curve, there's a point of maximum profit, and you can see that it's kind of there, but it's not exactly the same there for the three different genetic correlations. But nevertheless, for this set of parameters, it's saying that our optimal level of phenotyping is when we're spending around about $3 million a year on phenotypes, okay? So the point is there is a maximum and we can find it. Now, and we can model a situation where we suddenly say, oh, well, let's put in a really, really expensive trait and see what that does to it. Here I've added a trait, the yellow line up the top, which is methane, very expensive. And what it's meant is we can still find an optimum, but it'll be at a higher level of investment. And that'll depend on what the value of making improvements in methane is as well, but it takes account of its cost. So we can work out the point of optimal phenotyping. And probably don't need to go through that. I will make the observation at the bottom. If we were looking at the, say, the New Zealand sheep population or the Australian sheep population for that matter at the moment, and we did this by actually looking at the accuracies for the breeding gold traits, I would be virtually certain that we would find that we are quite a long way below the optimal level of phenotyping at the moment. So, and that's the sort of analysis that the beef and lamb team can do. They can look at the accuracies across the entire data set for the different gold traits for the different breeds, and then basically work out, well, if we could increase the accuracy for, let's say, maternal worth, for example, how much is it worth to do that? What would we have to do to get there? So that's the first part of what I'm talking about, is just the idea that we can find the optimal level of phenotyping. Now I want to just talk a quick few minutes about basically how to share the costs of the phenotyping. I'll introduce this point now. If we've got a genomic selection situation where a bunch of breeders are doing all the investment in recording, but a whole bunch of other people are just doing genotyping, then all the costs are sitting with the breeders and everybody else is basically getting a free ride. That's why it's called a free rider problem. And it's just not sustainable, basically. It's likely to lead to reducing investment in phenotype. The way I think about this stuff is not to say that all the phenotyping in the future in a genomic selection model will be done by people like the present day ram breeders. There are probably some ram breeders will continue doing phenotyping. Others may choose not to. There'll be probably some data will come from research places, some might come from processors or special, even some commercial operations. But the point is we can look at what phenotypes are there, how much it costs to get more of them, and work out how many we want. I now just want to show you a way of thinking about sharing the costs of that phenotyping, and it's based on trying to make sure that everybody involved in the system, whether they do phenotyping or just genotyping, everybody is getting the same return on investment, the same amount of accuracy per dollar spent. And I've got magic thumbs. I showed this morning. It's basically intended to convey the idea that we've got people represented by the green buckets who are doing phenotyping. And the size of the buckets is kind of meant to convey high accuracy, expensive phenotyping, which is the green bucket up the top, down to low accuracy, lower cost phenotyping, which is the small bucket at the bottom. They've got costs and they generate accuracy. All that the data that's represented by the green buckets is contributed to the reference, which is the wishing well. And then over here we've got people in the blue buckets who just genotype. That's all they do. And they get some accuracy, it costs them a certain amount of money, and the idea is that we're going to basically put a levy on the genotyping, which is the red arrow, that will collect funds that go back to the green buckets, okay? And the intention is that everybody ends up in a situation where the accuracy they achieve is that per dollar is the same, no matter whether they're the small bucket, the middle bucket, the large bucket, or the blue bucket, okay? And I just made a couple of approximate New Zealand scenarios where I've got high expense, high accuracy phenotyping, sort of middle expense, middle accuracy, low expense, low accuracy phenotyping, and I've got 107,000 animals in total across the green buckets, and I've got 2.5 million animals being genotyped represented by the blue bucket. So the green over there is the reference, 107,000 animals, and the genotype is 2.5 mil. I stress I didn't try to mimic the current situation of how many people are doing phenotyping and genotyping. I sort of made up an example which I thought would be reasonable, a relatively small number of people doing the top green bucket and larger numbers doing the other ones. But I'm not trying to defend this as exactly what it would look like for New Zealand, but it certainly illustrates the principle, I think. But in this situation, given those accuracies and costs and so forth, we would end to ensure equal return on investment for everybody, we would need to impose a levy of 83 cents per genotype on the blue bucket, and we contribute back to the green buckets either $67 per animal or $22 or $13 per animal, depending on which bucket it is. And I haven't shown it on here, but it means that everybody over there, the green buckets, is basically getting back about 45 cents in the dollar spent. So they all get the same proportional rebate, but importantly, they're getting the same accuracy per dollar as the people in the blue bucket. If we increase the size of the genotype only populations and we double it, we halve the levy that we need to apply, so it's gone down to 42 cents. And we change the amounts that are being distributed back by a small amount. And we can illustrate that a little bit more just to show the effects of scale. As we go down the columns, we've got a bigger and bigger genotype only population, the blue bucket. The levy that we need to impose gets smaller because there are more people being spread across that cost. And that applies whether we're talking about a kind of low overall level of investment or a high overall level of investment, which is this side here. But also as we go down the columns, the rebate that goes back to the green buckets gets bigger. The bigger the population is, the bigger the amount of money going back to the people who are doing the phenotyping. But all we've done is we've shared the costs of phenotyping across everybody who's using them in such a way that everybody is getting the same return on investment. So just to summarise what I've tried to say is it's possible to work out the optimal level of investment at an industry level. Beef and lamb could do that by looking at the current levels of accuracy for different traits. And you can see, are we close to the optimum for one or more traits? Are we a long way away from it? That starts giving you a basis of thinking about how you might get more phenotypes. I think it's relatively straightforward to share the costs equitably across the entire system. The maths behind what I've done is not very complicated at all, but it does mean a whole of industry approach. You've got to kind of have a look and say, this is the accuracy scenario for all the traits that are important across the different breeds. What's it look like? Where would we like to improve it? I think that's something that beef and lamb could generate as a kind of report and circulate and have as a basis of conversations pretty easily. It's, for people like me, it's really, really fascinating. It's almost as fascinating as genetic trends, but we're not talking about them right now. But, you know, nerds, anyway. It requires a whole of industry approach. It's lots of value in sharing what's happening with those parameters, what's happening with the accuracy for different traits, what would be the cost of increasing the accuracy for different traits. And I think it really sets up a basis for regular consultation just to see what the story looks like. What happens if the price of genotyping goes down a bit, for instance, or we get a new technology for measuring something that's previously been expensive. So it can become quite a dynamic approach, but it can be quite transparent and simple. The kind of reporting that David was talking about earlier this morning with NPROVE, you could imagine that sort of reporting for the accuracy scenario for genomic selection as a basis of meetings like the Sheep Breeder Forum. The last couple of points that I'll make relate specifically to where breeders fit into this, and it's a kind of segue for Jason. The thing that I think is so important about the sharing of the costs bit is that it explicitly recognises and rewards the people who submit phenotypes, and particularly quality phenotypes. So instead of going from a situation now where some people record quite well, some other people don't record so well, but there's no clear return on investment for phenotyping, and people sometimes complain about that a bit. Genomics, unfortunately, makes that problem way, way worse because it becomes possible to get breeding values without doing any work, which is what I'd be doing if the opportunity presented itself. There are people who are seriously good at phenotyping and love doing it. They should be explicitly recognised and rewarded, and this system does it for them. The second thing is it gives breeders the opportunity, in a sense, to focus. Some might like to focus mainly on phenotyping and let someone else do the breeding or the marketing side of things. So it sort of disentangles recording from selection from marketing, and that, I suspect, is an attractive thing for some people. It also, by getting the reference population to the optimal size, it just makes it possible for basically everybody to be making faster progress than is currently the case. That generates more money for the industry, and some of that flows back to breeders. So it's a kind of virtuous circle. Jason.
Right, thanks Rob.